of a function in a matrix space. Suppose we have two functions xt and yt. Then a function f from x to y is said to be continuous at a point x belonging to x if for every sequence xn in x converging to x we have a sequence fxn converging to fx in y. From the diagram we see that in set x we have a sequence xn converging to x, and in set y we have a sequence fxn converging to fx. fxn is the image of xn under f, and fx is the image of x under f. We say that f is continuous on a subset A of x if f is continuous at each a belonging to A. Means the function is said to be continuous on the subset A if it is continuous at each point of this subset A. Now we give example of a function which is continuous and closed but not open. Let us define a real valued function f as fx equal to 0 if x is less than 0 and x if x is greater than or equal to 0. Clearly f is continuous function. Also, if we draw the graph of this function, there is no break in the graph of the function. Also, from the definition we can verify that this is a continuous function, but this is not closed. This is closed. This is a closed function but not open. For a subset f on the real line, we can write f equal to f1 union f2, where f1 is equal to f intersection minus infinity to 0, because fx is 0 for all the values of x for which x is less than 0, means minus infinity to 0, and x for all the values of x greater than or equal to 0, means for all the values of x from 0 to infinity. 0 is included here but 0 is not included here. So we have written a subset f of a real line as f1 union f2, where f1 is f intersection minus infinity to 0. 0 is not included here, and f2 equal to f intersection 0 to infinity. And we can write f of f as f of f1 union f of f2, where f of f is equal to f of f2 if f1 is equal to 5. If f1 is equal to 5, then f of f1 is also 5. So f of f2 means f of f2 is x greater than or equal to 0, means f intersection 0 to infinity, whereas f of f is equal to singleton set 0 union f2 otherwise. So f1 is 5, f of f is f2 if f1 is 5, and this is f of f is singleton set 0 union f2 otherwise. In both the cases we say that f is closed. It means this function f is closed. However, we see that f is not open, as the image of open set minus 1 1 under this function is 0 to 1, because for values minus 1 to 0 it is 0, and for values 0 to 1 it is 1. So it is 0 to 1. So the image of minus 1 to 1 is semi-closed interval 0 to 1. So this is not open. This is a semi-closed interval. So we can say that this function fx, for which the value of f at x is 0 for x less than 0 and x if x is greater than or equal to 0, is a continuous function, and it is a closed function, but this is not open. Now how will we find the distance between two subsets? Let A and B be two non-empty subsets of a meeting space X. We define the distance between two sets A and B as infimum of the distances between A and B, where A belongs to A and B belongs to B. So to find the distance between 2 points, we calculate the infimum of the distances between the points of the sets A and B. Now what is homomorphism? Let X and Y be metric spaces. A function f from X to Y is said to be a homomorphism if f is a bijection. Bijection means it is 1, 1 and on 2, and both f, where f is a function from X to Y, and f inverse, which is a function from Y to X, are continuous. So for the function to be called homomorphism, first of all f should be bijection, means it should be 1, 1 and on 2. Secondly, f should be continuous, and also f inverse should be continuous. We say two spaces X and Y are homomorphic if there is a homomorphism from X onto Y. This homomorphism is something like isomorphism in the theory of groups or linear isomorphism between vector spaces. For example, the metric spaces semi-closed interval 0 to 1 and 1 to infinity with the standard metric induced on it are homomorphic via mapping X to 1 upon X. We see that this function is bounded while this is not bounded. Therefore, we conclude that property that a metric space is bounded is not a topological property. Similarly, any Cauchy sequence in this set converges to a point in this set, while there exists a Cauchy sequence in this interval 0 to 1 which is not convergent in 0 to 1. It means the property that every Cauchy sequence in a metric space is convergent is not a topological property. Suppose we consider a function f from open interval 0 to r, which is defined as fx equal to 1 upon x. It is easy to see that this function is continuous at each point a belonging to 0 to 1. Here 0 is not included. So this function is continuous at each point in the open interval 0 to 1. So what we would like to analyze is the behavior of delta required to prove the continuity of f at x as x varies from 0 to 1. As x tends to 0, we see that this function fx goes to infinity. Thus it is clear that if you want to control the value of fx dash for x dash near to x, nearer x to 0, smaller the value of delta. That is, if we want to assert that fx dash is within epsilon distance of fx, then we have to restrict x dash to smaller and smaller open intervals around x as x goes nearer and nearer to 0. It means for given epsilon greater than 0, we cannot make a single choice of delta which will work for all x belonging to this open interval 0 to 1. And this motivates us to give the definition of uniform continuity. So what is uniform continuity? Suppose f is a function from xt to yd. xt is one metric space and yd is another metric space. We say that f is uniformly continuous on x if for given epsilon greater than 0, there exists a delta greater than 0 such that whenever x1 and x2 belongs to x are such that distance between x1 and x2 is less than delta, we have distance between fx1 and fx2 is less than epsilon. Here fx1 is image of x1 under f and x2 is image of x2 under f. So whenever the distance between dx1 distance between x1 and x2 is less than delta, and we have distance between fx1 and fx2 less than epsilon, in that case we say that the function f is uniformly continuous on x. So we notice that the continuity of f at a point is discussed, then we are concerned only with the values of the function near the point under consideration. But when we wish to say that function is uniformly continuous on its domain, we need to know the value of f on the entire domain. So it means the continuity is a local concept, while uniform continuity is the global concept. Suppose, for example, we define a function from 0 to infinity to r as fx equal to 1 upon x. We estimate that modulus of fx minus fy is equal to 1 upon x minus 1 upon y, which comes out to be modulus of x minus y upon xy, and this is less than or equal to modulus of x minus y, because x is greater than or equal to 1 and y is greater than or equal to 1. So if delta greater than 0 is given, then we may choose delta equal to epsilon, hence the function is continuous. But on the other hand, if we define a function g from 0 to 1 to r, here the domain is 0 to infinity, here we have taken 0 to 1, and the function is same, gx equal to 1 upon x, we expect trouble at a point near 0. Hence g is not uniformly continuous on 0 to 1s. The natural choice of points near to 0 are 1 upon n. If we consider x equal to 1 upon n and y equal to 1 upon m, where n is not equal to m, then modulus of fx minus fy is equal to n minus m is greater than or equal to 1. It shows that g cannot be uniformly continuous on open interval 0 to 1, because if it were, for epsilon equal to 1, there exists delta greater than 0 such that modulus of fx minus fy is less than 1. So given a delta, we can choose n greater than or equal to 1 upon delta and let x equal to 1 upon n and y equal to 1 upon 2n. Then modulus of x minus y is delta, but modulus of fx minus fy is equal to n. So it means this function g is not uniformly continuous. Now one more result. If xt and yd are metric spaces and f is bijective mapping of x onto y, the following statements are equivalent. First one is f is homomorphism. Second is f is continuous and open. Third is f is continuous and closed. F is homomorphism. F is homomorphism means f is bijective, means f is 1 1 and onto. This is also given to us. Secondly, f and f inverse are continuous mappings. So suppose first we will prove 1 if and only if 2, means if f is a homomorphism, if and only if f is continuous and open. First of all, we assume 1 to be true. It means f is a homomorphism. F is a homomorphism means it is bijective and f inverse are continuous. So it is already given to us. Now we need to prove that f is open. So let G be inverse mapping of f, and so that we write f inverse equal to G and G inverse equal to f, because inverse of f inverse is f only. Since f is a homomorphism, f is 1 1 and onto, and f inverse are continuous. So G is also 1 1 and onto. Suppose G is an open set. Since G is continuous, because it is given to us, because f is a homomorphism, it means f inverse is also continuous. So the F inverse continuous means G is continuous. So it means G inverse G equal to Fg is open, because by the definition inverse image of open set is open. So it means F is a open mapping. It means 1 implies 2. For the converse part, assume 2. F is continuous and open, then F is homomorphism. So it is given to us that F is bijective, also continuous and open. Now we have to prove that G equal to F inverse is continuous, because all other properties of homomorphism are already satisfied. Let G be any open set, then F of G is open by hypothesis. It means that G inverse G is open, so G equal to F inverse is continuous, because we know that inverse image of open set is open if the mapping is continuous. So it means 2 implies 1. So we have proved that if F is a homomorphism, if and only if F is continuous and closed. Now we will prove 1 if and only if 3. Means if F is a homomorphism, if and only if F is continuous and closed. Let H be we assume 1. Let H be any closed set. It means its complement is open, means X minus H is open. Since G equal to F inverse is continuous, because F is a homomorphism, it means G inverse X minus H is open, because inverse image of open set is open under continuous mapping. It means G inverse X minus H is equal to Y minus G inverse H. Hence Y minus G inverse H is open. It means G inverse H is closed. G inverse H is closed, or we can say that H is G inverse H is closed, means F of H is closed. It has been shown that F of H is closed. Here it should be F of H. F of H is closed. It means F is a closed mapping. Here it should be F. Here also it is F. Or this line is not required also. This implies F is a closed mapping. Now for the converse part, we assume 3. And we will show that G equal to F inverse is continuous. Because we have to prove that F is a homomorphism, all other conditions are already given to us. Let G be any open set. It means X minus G is closed. Since F is a closed mapping, this is given to us, therefore F of X minus G is equal to G inverse X minus G, because F is equal to G inverse, and this is equal to Y minus G inverse G is closed. It means this is the complement of G inverse G, means G inverse G is open. Thus the inverse image under G of every open set is open. It means G equal to F inverse is continuous, or we can say that 3 implies 1. So we have proved both the parts. Thank you.